Alright, so Factorial ANOVA is really just an expansion of a one-way ANOVA. In a one-way ANOVA, you have one independent variable, but you would use a factorial ANOVA when you have more than one independent variable. Importantly, these independent variables need to be categorical. That is, they need to be nominal or made up of categories, such as gender or drug versus placebo. They themselves can't be continuous, or you would have to use regression. But when you have one or more categorical independent variables, you're going to want to use Factorial ANOVA. Factorial ANOVA tests what's referred to as the omnibus null, which means that the means of all the different groups are exactly the same. So male mean is the same as the female mean, or the drug mean is the same as the placebo mean, etc. Importantly, though, it can also test for groups that vary on two or more independent variables. So unlike one-way ANOVA, which can only tell you whether the two groups are different, this can tell you whether subsets of groups are different. So for example, are males in the drug condition different than males in the placebo condition, different than females in the drug condition, different than females in the placebo condition? So it allows us to essentially stack our independent variables, which is going to be very important for something referred to as interactions that I'll show to you here in just a second. However, once you're done with that Factorial ANOVA, because it's testing the omnibus null, that all the means aren't the same, if you want to know any particular means differ, you're going to have to go in and do post hoc tests or contrasts. Essentially what these do is they compare subsets of your data. So they can test specific hypotheses, like are males different than females, rather than are males with drug or placebo different than females with drug or placebo. So essentially you can go in and look at more refined hypotheses in your data, rather than just the general omnibus hypothesis that at least one of the groups is different from the others. This allows you to investigate further and interpret what you're finding with your Factorial ANOVA. So if you get a significant Factorial ANOVA, you might wonder what's driving that. Is it perhaps just that males in the placebo condition are completely different than all of the other groups, or is it that all the groups vary in some way or some subset of those? So in order to figure something like this out, you'd have to use post hoc tests or contrasts. Okay, as I mentioned before, Factorial ANOVA is great because it allows you to look at what's called an interaction. Now, an interaction should be thought of as basically it's when the effect of one variable depends upon the level of the other variable, right? So a classic example of this, a very easy way to think about it, sort of a canonical example, would be birth control pills, right? If you give females birth control pills, they're going to have a very different outcome than if you don't give them to them. However, if you give birth control pills to males, they're not going to have any effect at all, right? So that would be an interaction. The effect of one variable, birth control pills versus non-birth control pills, depends crucially on the level of the other variable, whether you're giving it to males or you're giving it to females. Now, graphically, it's helpful to think of this as basically when the lines cross on the graph. So you'll see here in the example I have on the slides that for some made-up experiment here, that males with placebo are lower on our dependent variable than males who have been given our drug. However, you'll notice that females show exactly the opposite pattern. Females are lower with the drug than they are with the placebo. This is what an interaction is always going to look like once you take away the effects of other variables. So when you see crosses in the graph like this, what they're showing you is when the lines cross, the effect of one variable depends upon the level of the other variable that you're looking at. Now, there's three kinds of Factorial ANOVAs that you can do. First, you could do a between subjects Factorial ANOVA. Now, this is just a classic experiment where you give one group one treatment and another group another treatment, and you compare them, right? So this would be very similar to a typical one-way ANOVA, just with extra independent variables. You can also use it within subject design, where you compare different conditions within the same subjects, just like with all of our other tests, like the dependent t-tests. So here, for example, you could test subjects before they've taken, say, some math course, and then you could test them after they've taken the math course and compare to see if the math course had some effect on, say, their ability to do SAT mathematics or something like that. And finally, you can do what's called a mixed model ANOVA. Now, mixed model ANOVA is a very fancy design in which some of the variables are within subjects and some are between subjects. So, for example, let's say you use this math course for males and females. The male-female independent variable obviously has to be a between subjects variable because you can't assign people to different sexes and then manipulate it. However, the math course itself would be a within subject variable if you gave every participant, if you tested them before they took the said math course and then after they took the said math course. So in this design, you would need to run a mixed model ANOVA with gender as a between subjects variable and with the math course as a within subjects variable.